session, session 2A. We will have 5 papers in this session, and the first session the first paper will be given by Meran Goli, who is a postdoctoral researcher at University of Bremen and in German Research Center for AI, also in Bremen. In Germany, he got his bachelor from University of Shahed Beheshti in Tehran in Iran, and a master from University of Tehran also there. And he has a PhD degree from University of Bremen in Germany from 2019. He is interested in system level design, verification, security validation, machine learning techniques, and approximate computing. So let's play Mehran's presentation. And I'm not sure sound works now.
Mehmet, sound doesn't work. You have to unmute yourself.
Okay.
Hello everyone, my name is Meran Goli, and today I'm going to present our paper entitled ASCII Automatic Fault Localization of System CHLS Design using Hybrid Accurate Rank Ordering Techniques in ICCD 2020 conference. The increasing functionality of digital systems and reduced time to market constraints push designers to model systems at a higher levels of abstraction than the traditional register transfer level RTL. Hence, high-level synthesis at the electronic system level is being increasingly adopted by the semiconductor industry to boost the design productivity. HLS design are typically developed using System C language as a de facto standard at the ESL and can be automatically synthesized into RTL. This means that HLS designs are reference model for lower levels of abstraction. Thus, their verification is of utmost importance as undetected fault may propagate to lower levels of abstraction and become very costly to be fixed. Although lots of progress has been made in terms of correctness assurance of System C designs, providing an automated debugging solution has received less attention, mainly due to its object-oriented nature and the complex language construct and semantics. In general, the debugging process consists of 2 main steps, which are fault localization, meaning the identification of possible faulty locations that eventually lead to design failures, and fault correction, which means locally modifying the functionality of the identified portions. The fault localization is considered as the most time-consuming step in the debugging process, and its quality affects the fault correction step. In this work, we focus on the fault localization of System CHLS designs that is the critical step of the debugging process and typically takes significant amount of time and effort from designers. In this slide, we explain challenges of fault localization in System CHLS designs using a motivating example. Consider the 2-stage pipe design implemented in System C. The design includes 2 modules, M1 and M2, and performs a set of algebraic operations to generate the final results in 2 steps. Here, we also assume that the only reference that is available for designers is the correct value of final outputs as a reference result. Now, consider the scenario that designers made 2 mistakes when implementing the design. First, an incorrect assignment where the definition of variable gen b is incorrectly implemented. Second, an incorrect operator where the local variable temp2 is incorrectly defined. After executing the design, they found that the value of final outputs out1 and out2 of module M2 is incorrect. Therefore, an important task is now debugging, which means localization of the faults and then fixing them. However, fault localization of System C designs is very challenging, as the C++ compiler cannot detect these types of faults as they are functional faults and are not related to the C++ or System C syntax. Monitoring the simulation behavior of the design is very time-consuming, as it requires to manually trace runtime values of all design variables. Therefore, it does not reduce the number of fault candidates and the search space. Since no reference model or a basic specification of the motivating example is at hand, the formal methods are not applicable. Moreover, as System C lacks formal semantics, translating System C source code into a formal language is not a trivial task. The existing C-based debugger methods are not applicable as they do not support System C construct, data types, and semantics. And finally, simulation-based method at the ESL, focusing on visualization and monitoring of the design behavior and not fault localization. Our proposed methodology, ASCII-RO, to address this problem consists of two main phases, which are hybrid program slicing and ranking analysis. Before going to the details of the approach, we need to know what is the program slicing. The program slicing technique has been introduced for the first time in the software domains to identify parts of a program which have an impact on a selected set of variables. Parts of the program that do not affect these variables are eliminated, and hence a reduced set is obtained. This reduced variable set is called a slice. To perform program slicing, we first need to translate the design into a set of formal representation. We consider two data structures, which are correlation graph and Hammocks graph. The correlation graph describes how different variables of the design are related to each other, and the Hammocks graph specifies how different statements of the design are related to each other. These are done by analyzing the abstract syntax tree of the design using Clang compiler. After generating these data structures, we perform program slicing, where static slicing is performed on correlation graph to identify the dependency of a given output to the design variables, and dynamic slicing is performed on Hammocks graph to identify those variables and lines of code that associate to the faulty output for a specific input test. In the second phase, results of the static and dynamic slicing are combined to create a confidence score for each variable of the designs in a reduced set of lines of code. The confidence score is calculated based on two parameters, which are the probability of fault occurrence on a variable derived from the static and dynamic slicing. The first step of performing the program slicing is to extract the correlation graph from the abstract syntax tree of the design. Once the correlation graph is extracted based on the cones of faulty outputs, the correlation graph is sliced into some regions. In the case of the motivating example, 7 regions are created. The identified regions in a correlation graph are completely independent from each other, and each node of the graph is only member of one of the regions. For example, regions R1 only includes nodes of correlation graph that belongs to cone out 1. In the second step, the Hammocks graph representation of the design is extracted by analyzing the abstract syntax tree of the design. The static slicing of the Hammocks graph for a set of faulty outputs is performed by identifying all nodes of the graph on which the outputs are dependent. The node in the Hammocks graph is considered as a dependent node to a given output if the corresponding statement of this node has at least one variable that is located in the cone of the output. Black circles in this figure show statements that influence out1 and out2, while white circles show statements that do not have any impact on them. The executed statements are obtained by running the program with the input test that cause faulty outputs. The dynamic slicing is performed by finding the intersection of the static slice of a Hammocks graph and the executed statement. The ranking analysis is performed to calculate the confidence score for each variable of the design and consequently a reduced set of lines of code. The confidence score is calculated in 2 steps, static and dynamic ranking. The goal of a static ranking is to specify the exact fault occurrence probability on nodes of correlation graph. To do this, we calculate the probability of fault occurrence for each region combination and subsequently calculate the probability of fault occurrence on each node of the selected region. To improve the confidence score of each variable, a similar probability analysis is performed on the region representation, including nodes that are obtained from dynamic slicing results. In our motivating example, after performing dynamic slicing, node N9 is eliminated from R1 as its corresponding statement was not appeared in the execution time. The probability of fault occurrence for each node is added to the confidence score of its corresponding variables. By this, we have 4 classes of variable candidates, where the actual faults are in the first 2 classes, including 5 variables. In this slide, we show the results of applying ASCII-RO to different types of System C designs for localizing single fault and multiple faults. As can be seen in this table, In case of single fault, ASCII on average reduces the search space by 82% in terms of line of code and 78% in terms of the number of candidate variables. In case of multiple faults, 76% in terms of lines of code and 71% in terms of the number of candidate variables reduction were achieved. The best case reduction results are related to the packet switch, RISC, CPU, and LZW encoder benchmarks, where up to 96% reduction in search space was achieved. In comparison to the pure compilation and execution time of each design, the execution time of ASCII is in the same range, that on average, it takes 20 and 22 seconds to localize single fault and multiple faults, respectively. As a conclusion, we introduced the first system CHLS fault localization approach at the ESL. ASCII take advantage of semi-formal techniques to provide designers with a reduced order of potential fault candidates. We target the common modeling mistake affecting the functionality of System C designs, such as fault state transitions, incorrect assignment, and incorrect operator. And finally, experimental results show the effectiveness of our approach in localizing even multiple faults with a high confidence in a short execution time. Thank you for your attention and have a nice day.
So, thanks.
Oh.
Are there
Sorry.
any questions? Oh, 30-minute workout we can do. Very good. Are there any questions before there is the workout?
Hello, everyone.
I can't see because of.
So I see nothing in the chat yet. I also don't see any hands in the participants, but maybe let me ask something. In this results slide, which had this big table with lots of three-letter abbreviations, can you explain once more what precisely what was evaluated? I mean, what is this method trying to optimize precisely?
Hi to everyone. Can you hear me right now? Okay.
Yes.
So the point here is that for this debugging task, we try to reduce the search space. Basically, when there is a fault in the designs, designers try to find the lines of code that is related to this fault that happened. But basically, this is kind of like a black box analysis because we only have the reference result and also the faulty output. So we don't have anything about what's going on inside of the design and where is the fault, basically. So if we can reduce the lines of code for verification engineer or designers, and also the number of variables. So in this case, we limit this search space for designers, and they can precisely goes to the specific part of code or lines of code, and this is like they can gain lots of time. And in this case, they can quickly access to the part of the designs that is really the fault happened there. So for example, if you have like 10,000 lines of code, we just reduce this search space to 200 lines of code. Or like also the number of variables as well.
And this FLR is what is what divided by what? Is some range?
Right. This is like this is the percentage that we reduced in comparison to the whole search space that we have. For example, the lines of code is the initial search space, and basically how much this CFL, or for example, this FLR is the reduction on the whole search space that we have.
What happens if you have only one output, or if your design has only one output?
So this is the point here is that this is kind of limitation for all the debugging methods that is based on some kind of formal analysis that we also had. Because when we have only one output, here is pointed the whole lines of code are in the cone of the faulty output. So we can from the static phase, we cannot have basically the search space reduction. But here the dynamic aspect of our design, our method basically help us. In this case, the dynamic part only shows the lines of code that are also appear in the execution time. So in this case, we can still get reduction in the search space by dynamic analysis. And basically, this is the advantage that we use a hybrid method instead of pure static analysis.
Are there more questions or comments? If yes, please unmute your mic. I don't see anybody. I also don't see any questions in the chat, because you can also ask in the chat and then I can read them out loud. Okay, if this is not the case, then I would say let's thank the speaker for his recording and the discussion, and let's move to the second talk. So the second talk, wait, before you started, let me introduce the speaker. So the second talk will be given by Leonid Yavits. Leonid received his master and PhD from Technion in Israel. And he is interested in non-von Neumann architectures, in accelerators, and in memory processing. During his industry career, Leonid co-founded a few startups, which were acquired by multinational corporations like Broadcom. He co-authored a variety of patents and research papers on SoC and ASIC, and also he received a number of best paper recognitions at computer architecture and high-performance computing venues. And today he will tell us about Wolfram. So, Leonid, the floor is yours.
Hello and welcome everybody. My name is Leonid Yavits. My co-authors are Luis Orosa, Suyash Mahar, Joao Ferreira, Ran Genusar, Matan Erez, and Onur Mutlu. I'm going to talk about enhancing wire leveling and fault tolerance in resistive memories using programmable address decoders. Resistive memories such as PCM face a number of unique challenges. The first challenge is the finite write endurance, which means that the memory cell lifetime is limited. The other challenge is the high non-uniformity of memory access patterns, which means that some memory cells are written much more frequently than others, which in turn means that those cells are likely to fail earlier. Yet another challenge is non-uniform endurance due to process variation, which means that some cells are manufactured weak, so in turn they have a greater chance to fail sooner. There are two state-of-the-art solutions to those problems. The first solution is wire leveling, which is designed to flatten the memory access non-uniformity. The second solution is fault recovery, which is designed to work around the failed memory cells. However, combining those two solutions proves to be quite challenging. Fault recovery typically maps out memory locations, which means logical addresses associated with failed cells. However, wire leveling assumes that the entire uninterrupted address space is available. Accounting for mapped out addresses proves to be very complicated. In the bottom line, wire leveling and fault recovery do not work well together. Before I move on to the Wolfram, I would like to remind everybody how a conventional address decoder works. In this figure, you see the concept of conventional NAND address decoder, which is composed of an array of NMOS transistors, where every row is associated with a memory row, and every column is associated with an address bin. In conventional address decoders, addresses are hardwired to memory locations, which means that address 0 necessarily points to memory row 0, address 1 necessarily points to memory row 1, and so on and so forth. Now I would like to introduce the programmable resistive address decoder. It is still composed of the array of NMOS transistors. and we add a pair of resistive elements that connect the gate of each NMOS transistor to the address bit line and inverted address bit line, which allows addresses to be programmed into decoder rows by programming those resistive elements. This means that in programmable resistive address decoder, addresses are no longer permanently tied, no longer hardwired to memory rows. Instead, logical addresses can be programmed into any physical location. Using the previous example, logical address 0, instead of pointing necessarily to memory row 0, can now be programmed and point to any memory row. The wear leveling in Wolfram is based on programmable resistive address decoder. The write access, instead of being made to an address permanently associated with a certain physical location, is mapped out to a random physical location. This remapping is achieved by programming the logical address alongside data, where address is stored in the address decoder row and the data block is stored in a collocated memory row. Since this new random physical location is not necessarily empty, we need to constantly swap the content of memory locations. Since such swap operation carries some performance and energy overhead, we don't remap every write access. Instead, we do the remapping periodically, or rather, we remap each access with a certain probability, which is much lower than 1. And here you have a little virtualization that shows how a repeated write access to the same address, the same logical address, gets distributed nicely and uniformly all over the entire memory space. For the fault recovery, we use a similar approach. If a memory row fails due to some failed memory cells, we remap the logical address associated with the failed row to some other physical location. The decoder entry associated with the failed row is blocked using a specific pattern so that this location is never selected again. Since we never map out the logical addresses, there is no need to account for mapped out addresses, which, as you remember, is the major problem of combining state-of-the-art wear leveling and fault recovery. There are 3 evaluation items. The first evaluation item is memory lifetime. On vertical axis, you have the memory capacity in percent. Memory capacity means the fraction of memory which is still operational. On horizontal axis, you have the lifetime measured in months. We compare Wolfram with the combined wear leveling and fault recovery solutions for wear leveling, we're using security refresh. And for fault recovery, we're using the error correcting pointers. As you can see, Wolfram with no error correction capabilities outperforms security refresh equipped with baseline error correction capabilities. And for Wolfram combined with error correction, it strongly outperforms the security refresh combined with full-blown ECP error correction. The second evaluation item is performance and energy overhead. On the vertical axis, you have the overhead in percent. The horizontal axis is the CPU spec 2006 benchmarks. And as you can see, the average delay and energy overheads are just short of 0.5%. The third evaluation item is the wear leveling speed. Here you see the distribution of per row write count, which means the number of writes made into each row of memory array. In ideal wear leveling, the distribution would be one single vertical bar, meaning the same exact write count in every memory row. As you can see, Wolfram shows a much narrower distribution, which is better, closer to the ideal distribution, where the security refresh has a much wider distribution, which means that its wear leveling speed is much lower. Why is wear leveling speed important? Because when the distribution, when the endurance variability is very high, the weakest memory cells may fail before the wear leveling takes effect. That's why wear leveling speed is of importance. To conclude, wear leveling and fault recovery are critical for resistive memories. However, combining those two proves to be quite challenging. Wolfram provides a holistic framework combining both wear leveling and fault recovery in an efficient manner. Wolfram outperforms existing solutions in both memory lifetime and wear flattening speed. This concludes my presentation. Thank you very much for listening.
Thanks. Questions? I don't see anything in the chat. If you have a question, please unmute your mic and briefly say who you are. So I don't see a question. So maybe can you explain? I mean, this sounded to me like it's a generic approach which is applicable to memories in general. Is there anything specific for like this PCM memories or for this resistive memories, or is it something which would also apply to normal memories?
Well, it can apply to many memory types, but there are limitations. So for example, in DRAM, you would have to use the same storage element which is used in DRAM array, which means you would have to use some kind of capacitive storage. The whole deal also makes sense in the case of hard errors because it corrects hard errors. It cannot correct soft errors. So if, for example, memory is prone to hard errors and it can allow using similar storage elements, then yes, it can be, it can be used, it can be applied to other memories than resistive memories. So maybe less in DRAM, but there is a very large variety of resistive memories, PCM, MRAM, and maybe NAND, where this can be applied.
Thanks. I still no see no external questions. So do we need to care about faults or defects in the decoder? I mean, the memory people always love decoders.
Yes, actually we do. Since we are using the same resistive elements to store address bits, they are prone to limited endurance related errors, just as the memory itself. But since resistive decoder changes its contents, it's been programmed much less frequently than the memory, maybe 1 to 100 or 1 to 200, 300 memory accesses. So the chance that resistive decoder will fail is much lower than the memory. And if it does, we basically use the same principle as we used to fix errors in memory. We use the same approach to fix errors in the programmable address decoder.
More questions. So, is somebody doing security? There is always a question whether there is something security related in those memories. Like, can there be some, I don't know, Trojan that is triggered by wear out, and can this somehow be controlled? Can this wear out leveling circuitry be manipulated to enable something? Do you have any opinion or any ideas on this?
Well,
I think there are some problems with
Lifetime.
connections.
oh, excuse me, can you hear me now?
Yeah.
Okay, so I'm saying, you know, definitely there is a problem of security, because when you have a memory with limited variability, with limited number of writes, someone, a malicious user, can use this feature to destroy this memory by, for example, repeatedly writing to the same address. So a programmable address decoder basically is basically supposed to make this this kind of attack extremely unlikely. I'm not going to say it's going to prevent it 100%. I cannot say that because I don't know. This work is not about security. I can make a claim, but it will definitely reduce the chance of that. And since this whole mechanism is happening within the memory array, it's not observable by operating system, for example. We don't know which addresses are being remapped where. This, of course, makes the position attack much more difficult as well. So this is about it.
But I mean, this is regarding this external attacker who has this memory in his hand and for some reason wants to destroy it. But do you think, I mean, if this functionality which you are adding, I mean, it's reasonably complex, do you think it's possible that there is like an insider attack, like a Trojan attack, somebody inserts into this, you know, into the circuitry something malicious which looks outside, like it is managing, you know, wear out and so on, but in reality it does something evil? Do you think this can be done?
Again, I'm assuming everything can be done, but since we're doing this in hardware inside memory array, it has extremely low visibility to anyone who comes from the outside. And well, I mentioned that it's basically done in hardware, so there are no remapping tables which sit in DRAM, for example. We're not using page tables. We're not using any software. So I suppose it's possible, but it makes it much more likely, much more difficult.
Any other questions? Last chance. Then I would say let's thank the speaker.
Thank you.
And so thanks, Leonid, for being available for this Q&A.
Thank you very much. Thank you.
Unfortunately, we cannot really have applause over Zoom, but assume that it happens in everybody's head.
Yeah,
so
I'll have to do.
then let's move to the third paper of this session, which is paper number 4, giving by Kong Li, who is senior staff engineer in Intel, who leads the development of various data center management solution. He is interested in machine learning and data-driven approaches to system modeling, management, and optimization. He co-authored 16 papers and 2 book chapters in this area. And before Intel, he was an assistant researcher on natural language processing and machine learning in Microsoft Research Asia, where he also published papers. And he is also a part-time instructor in Children's Computer Center, Children's Palace of Chinese Welfare Institute for Computer Technologies. So he is delivering also courses at weekends to that institution. So Kong Li, the floor is yours, or of your talks.
Everyone, I'm Tony from Intel. Today I will give a talk on DPCLS, improving partial catch line sparing with dynamics for memory error prevention. This is the joint work with Xiaoming Du. Here is the outline of my talk. First, I will briefly introduce the topic of DRAM reliability and errors. Next, I will describe the background on partial catch-line sparing and its weakness. After that, I will propose the improvement to PCLS with dynamics. The experimental results are then given, demonstrating that the DPCLS outperforms PCLS. Finally, I will give the concluding remarks. A dual inline memory module composes of a few DRAM devices organized in ranks. Each device contains a few banks, and each bank is a two-dimensional array of cells indexed by rows and columns. While we expect that the content read from the devices should be the same as that written, in reality, it may not. There can be multiple underlying causes, to which we refer as faults. For example, soft faults like particle strikes. When DRAM wears out, non-reversible hard faults get developed. Hard faults are found to be dominating in the field. In summary, DRAM is not reliable. To mitigate DRAM failures, error-correcting codes have been developed. ECC corrects the error bits in correctable errors. A side effect is that performance may get impacted given a relatively high CE rate. This is because the overhead in the complete path of error detection, correction, handling, and reporting. However, when errors coincide, the error pattern may go beyond ECC's capability. The coincidence then becomes an uncorrectable error. A UE typically leads to a system crash. As a problem at scale, it becomes one of the leading causes of failures in data centers. An alternative mitigation is to use the error correcting pointers. ECP detects cells with hard faults from repeat CEs and use spare cells to store the data content of the faulty cells. ECP alleviates error coincidence, therefore mitigating UEs. By replacing the data content before going for error detection, it also eliminates the performance impact from error handling. Partial catch-line sparing is an extension of ECP implemented in memory controllers. It operates the sparing at the unit of 4-bit nibbles. During memory access, PCLS identifies a faulty nibble from repeat CEs. Mapping from the faulty nibble to a spare entry in the sparing directory is then statically encoded. During a future write to the faulty nibble, PCLS also writes to the spare entry. During a future read of the faulty nibble, the content from the spare entry is taken for replacement before error detection. For cost consideration in memory controllers, the number of entries in the sparing directory is typically limited. Say, for example, 16 per memory channel in contemporary servers. When all the entries get filled up, its error prevention capability saturates. Here we show the error log of a channel from a server. In PCLS, the entry in the directory are filled up on day 10. Given error bursted from newly observed faulty nibbles on day 17, PCLS then failed to capture the burst. This indicates that PCLS error prevention capability is limited. Now we propose the improvement, dynamic PCLS. DPCLS is inspired by the observation of temporal localities in memory errors. The temporal localities are likely the combined effect of the temporal locality in memory accesses and the dominance of hard faults. Instead of the static assignment of spare entries in PCLS, our idea is to dynamically manage the sparing directory through admission of new faulty nibbles and eviction of old faulty nibbles. We use a simple first-in, first-out policy, treating the sparing directory as a circular buffer. Thus, PCLS tracks the hot faulty neighbors for error prevention. Here we compare the algorithm of PCLS and the DPCLS. Given a faulty neighbor detected in PCLS, the execution flow stops given a full directory. In DPCLS, we simply evict the oldest one and admit the new one. The change is simple and straightforward. To evaluate DPCLS, we use the dataset from a commercial cluster hosting internet services. They are the latest Intel Skylake and Cascade Lake servers. The workload is a mix of social network services, online data feeding, offline data analytics, and so forth. Data are collected over 1.5 months in last year. There are 0.3 million CEs from more than 100 servers. The data is used in experiments of trace-driven simulation. We first show the results of avoiding CEs with different port identification thresholds. We see that PCLS needs an adequate threshold, not to fill the entries too early or too late. In DPCLS, a small threshold value well captures the temporal localities. It avoids more CEs than PCLS does. Note that one type of UEs come from the coincidence with a random sort of error. The percentage of avoiding CEs then translates directly to that of avoiding this type of UEs. In summary, DPCLS performs better in avoiding errors. We next estimate the time period with performance impact due to a relatively high CE rate. We see that DPCLS with a small threshold reduces most of the performance impact. This indicates that by exploiting the temporal localities in CEs, DPCLS is especially effective in reducing performance impact from storms of errors. Finally, we study the case that demonstrates the weakness of PCLS. On the memory channel, we see that due to a smaller threshold in DPCLS, the directory gets filled up early on day 6. However, it continues to admit new faulty neighbors and evict the old ones, so that it captured the error burst on day 17. This study shows that DPCLS overcomes the weakness of PCLS. To conclude, we have proposed the dynamic PCLS approach to improve PCLS. DPCLS dynamically manages the spare entries in neighbor sparing. Experimental results indicate that DPCLS performs better in avoiding errors. This also results in a much better reduction of performance impact. Here is the end of my talk. Any questions or comments are welcome. Thank you.
Thanks. So, questions, comments? So, let me then start one more time. So regarding results, I'm not sure I understood everything. It was quite small on the slide, but it looked like the probability of failures or whatever it was for the non-dynamic case around 15%, and for the dynamic case, for the proposed one, around 20%, or maybe 19 to 22 or something like that. Is it really a critical improvement? I mean, is it if it fails every 5th time instead of every 6th time? Is it a big deal?
I think that this is about the percentages of errors that we can prevent it through partial catch-line sparing or dynamic partial catch-line sparing. And this way, we are able to avoid certain percentages of encountering uncorrectable errors in the future. So since this is a very small overhead in the memory controller, so this is regarded as worthy, and it has already been implemented in the servers.
Well, what happens with the other 80%, which got reduced now from whatever, from 85 to 80? But what happens with those other ones?
And the remaining errors currently are requested to be corrected using the error correcting code.
Mm.
And if it's something like a coincidence with a random error and it becomes an uncorrectable error, then the server just crashed.
Mm. And do we know how often that happens?
I think that changes from generation to generation. And it is expected that given the density of the DRAMs becomes higher, probably in the future, we will see a higher failure rate.
Mm. And any ideas what to do then? Maybe something
there
in
are
software?
other, there are other types of sparing technologies that can be complementary. For example, one can spare a bank dynamically, or one can use some software sparing technologies like page offlining. But those things need to be well coordinated with the existing, the most low-level things like PCRS. Otherwise, it would be a waste if there is a duplicate sparing habits.
So what would be in this case be like a coordination effort? I mean, what would be a good coordination? What would be a bad coordination? Or what should a software designer or designer of this software, what should he or she think about?
And this is an important topic that needs to be to have in the hardware and the software co-design. And currently, I think this kind of things are not well considered in the existing case with both software sparing and hardware sparing enabled.
So, any other questions or comments? Just unmute and ask your questions. It doesn't have to be only me who is asking all the time. Looks like this is not the case. Then thanks to Kong Li. Thanks for this presentation. Thanks for your answers. Yeah. Then let's move to talk number 4, which will be given by Romain Messier, who is a PhD student at INRIA in Bretagne Atlantique in France. He got his master in computer science and an engineering degree on signal and image processing and embedded systems in 2018 from University of Rennes #1, also in France. And his research is on fault-tolerant and network on chip for deep learning algorithm. So the floor is yours.
Hello, my name is Romain Mercier. I am a PhD student in INRIA Corporation. Today I will present you our work about the mitigation of permanent faults in network on chips through the use of a bit shuffling technique. First, I will begin by presenting you the context and the problematic related to our work. Since several decades, network on chips became the dominant paradigm for on-chips communication due to their high scalability and high bandwidth. To cross the network on chip, messages are divided into packets, which are themselves divided into fleets. Each fleet is sent one by one through the network on chips from a source IP towards the destination IP. As the messages exchanged by the different IPs transit on the network on chip, this one becomes a critical system which needs to be enhanced against faults which can affect data fleets, also called payloads, or control fleets, also called headers. So, as mentioned on the previous slide, network on chips are susceptible to be faulty due to several external effects, such as, for example, component aging or radiations. With nanoscale technologies and power scaling, these external effects lead more and more frequently to transient or permanent physical failures in systems. In our case, we consider only faults affecting network on chip data path. Indeed, our crossbars, buffers, and interconnections have the largest area in the network on chip, they are more prone to error. Moreover, in this work, we consider the case where routers are impacted by several permanent faults. As shown in the figure 2, all fleets are impacted similarly by stuck-at or bit-flip faults when they cross the faulty routers. In this way, we propose the following problematic. How multiple permanent faults can be managed in network on chips. Some methods are available in the literature to handle permanent faults in network on chips, such as, for example, routing algorithms, reconfiguration methods, and redundancy techniques. But these methods have often a high hardware cost in terms of area cost, power consumptions, and latency. Moreover, the accumulation of several permanent faults with these techniques can lead to congestion and unreachable IPs. Then, these methods are not scalable in presence of multiple permanent faults. On the other hand, the approximate way is studied since few years in network on chips to reduce the hardware cost by reducing application accuracy. So, we decide to explore the approximate way through a bit shuffling technique. Bit shuffling techniques are already used in several fields. They are now under other names such as interleaving in telecommunication or scrambling in memory protection. Based on this, we propose a bit shuffling method targeting fault-tolerant applications to protect data paths in network on chip. This method consists to tackle faults by transferring them on the least significant bits to keep the most significant bits safety. Moreover, our method is able to handle multiple permanent faults. Now, I will present you the principle of our bit shuffling method in the next slides. So, to understand the principle of our method, we need to know how messages are formatted before injection in the network on chip. First, messages are split into packets, and these packets are themselves split into fleets which will be sent through the network. To cross the network, these fleets need control information, such as, for example, the destination. These information are contained in an additional fleet added in each packet. This fleet is called the header. Finally, to apply our method, we add an additional subdivision that we call subfleet. In this way, each fleet is split into several subfleets, which will be reconfigured to limit the impact of the permanent faults on the data. Our method is applied to the use of few blocks, the shuffler blocks, symbolized here in yellow with the letter S, and the deshuffler blocks, symbolized in green with the letter D. In the case presented in this slide, we consider the transmission of one packet composed of one header and two payloads which contain unsigned integer data. We suppose that the packet is sent through the faulty router from north to south. In this router, the faulty element, symbolized by the red hash, is the crossbar. When the fleet enters in the protected zone, it is reordered by the shuffling block to place the least significant subfleets on the faulty path. In this way, when the fleet crosses the faulty element in the router, the faults impact only least significant bits. And finally, before the router output, subfleets are reorganized at their original configurations by the deshuffler block. Thanks to that, we can see that the error on the output fleet is largely minimized by the shuffling, since the most significant bits are kept safety. Of course, the efficiency of the method is correlated to the subfleet size. Indeed, the method will be more efficient when the subfleet size will be reduced. So, as mentioned previously, our method necessitates two blocks to operate, the shuffler block and the deshuffler block. As shown in the figure 5, these blocks are set at each input and output of the router to protect efficiently the routers and the interconnections in the network on chip. The interarchitecture of these blocks, represented in the figure 6, shows that these blocks contain only multiplexers, which is managed by the simple register. This architecture allows for the shuffling and the deshuffling blocks to be executed in only one cycle with a short critical path. For that, the register indicates the configuration taken by the subfleets inside the incommit fleets. it is updated offline according to the fault localization provided by an external method, such as, for example, a built-in self-test. Now, I will present you some results obtained with our method to an approximate application. For that, we consider a mesh network on chip constituted of 4 routers where a memory and a core communicate between them. We use the XY routing algorithm and consider 32-bit fleets, which are split into 4-bit subfleets. The stack and fault model is considered in this experiment, and several bits are impacted to simulate multiple permanent faults on the loading path and the storing path. To test our method, we choose to use the Canins clustering algorithm. Through this application, we can notice on the figures 8, A, B, and C that the proposed bit shuffling method allows for the clustering error rate to be largely decreased. On the other hand, we can notice that the Hamming code has no effects on the clustering error rate since the number of faults is too high for this error correcting code. If we analyze the hardware cost of our method with the hardware cost of the Hamming code when they are implemented in the connect router of the literature, we can observe that the bit shuffling technique has a lower area cost and a lower power consumption. To conclude, during this presentation, we presented a low-cost method based on a bit shuffling technique to mitigate multiple permanent faults in network-on-chip data path. We demonstrated that this technique has a lower hardware cost and a better efficiency than the Hamming error correcting code in presence of several permanent faults. Moreover, the proposed method is able to handle multiple permanent faults contrary to the other techniques proposed in the literature, with no additional cycle and a reduced critical path. This is the end of my presentation. Thank you for your attention.
So, thanks. Questions or comments? I assume everybody has seen the 22 or so references. Okay, then let me maybe start again. So if I understand correctly, you remap the least significant bit of uncritical data like images to the faulty places, which and you know in advance that they are faulty because you have run self-test, and the self-test told you this bit doesn't work. Do you need to transfer them at all? Cannot you just transfer the reliable parts of it and just not transfer the fault effect at once? Like just reduce the precision? Would that work?
Yes, this method, the aim is to reduce the precision until certain limits, which are defined by the applications. So we don't correct the fault, but the remap of the subfleet position allow for the least significant bit to tackle the fault in which way we're keeping safety the most significant bit.
So, I mean, in, let's say, circuit design, people are, how should I say, not very enthusiastic about this approximate computing on erroneous hardware for the reason of early life failures. So if you have some bits which don't work, which have a stacked fault, then the question is, why is there a stacked fault? I mean, maybe you can somehow tolerate the stacked fault, but maybe there is a resistive bridge, and it will lead to effects on the neighbors of the stacked fault. So your system will, the reliability of your system will actually go down. Do you have any ideas in this direction?
For the reliability of the system, after we can extend the reliability of the proposed method by duplicate each bit, and in this way we added unused bits in each bit, and
with this unused bit, we can tackle the faults without impact data which are forwarded in the feed. So we can use this button without approximate computation in the NOx.
Mm-hmm. More questions? Let me check in the chat. Nowhere there. Nothing there. So maybe one last question. What happens if you do need to transfer something reliably? If you have instructions or if you have some data which are not images or image pixels or audio samples or something like that, are we lost then?
Sorry, I don't understand. In the case where the data types are not the same size of the feeds, is that?
I mean, like sensible data, such as instructions.
Okay.
How are they protected?
For the sensible data, we apply the same case that for the headers, which means that we decide to duplicate each feed. So in this way, we the packet, the length of the packet is multiplied by 2. But for each feed, we added so many unused bits that half of the feed can take us false to keep safety the most significant bits. For example, for 32-bit feeds, in this way, if we duplicate each feed, we can handle until, for example, 60 faults in the architecture, in theory.
Okay. Then maybe in the interest of time, I see that actually this session is a little bit shorter than I thought. Let me thank the speaker, and let's go over to the last presentation, which is given by Haoshan Guo, who is a PhD candidate from Louisiana State, and he is interested in performance and energy efficient AI accelerators. So, floor is yours.
Hello, good morning, everyone. Welcome to my talk. My name is Haoshan Guo. I'm a third-year PhD from Louisiana State University. I'm glad to introduce our work on accelerating attention-based neural networks here. The accelerator we proposed is ATT. My topic is a fault-tolerant rerun accelerator for attention-based neural networks. This talk consists of 4 sections in background algorithm, and the rerun will be introduced. Then following ATT design and hazard analysis, the third section will demonstrate the proposed strategy to address the hard fault issues. Finally, we provide the evaluation results. Traditional layers of neural networks can be classified into 2 types: spatial stacked layers and temporal stacked layers. Convolutional layers and fully connected layers are spatial stacked layers. Over the past 2 years, a new type of spatial stacked network has been proposed and has shown state-of-the-art performance in natural language processing. The new network is attention-based neural networks. The attention-based neural networks are stacked with encoders and decoders instead of convolutional layers or fully connected layers. Roughly, both the encoder and the decoder consist of 5 subblocks. The difference of an encoder and a decoder is the number of subblocks. An encoder has 1 QKB attention, 1 head merge, and 2 layer normalization, and 2 fully connected layers. By contrast, a decoder has 2 QKB, 2 attention, 2 head merge, and 3 layer normalization, and 2 fully connected layers. The QKB subblocks takes in the embedding matrix of a sequence and computes QKB vectors according to weight matrix. The attention scores each word of the input sentence against the other words in the same sentence. The head merge first subblock first concatenates output vectors from different heads Next, the concatenation vector is multiplied by a weight matrix. The layer norm performs the layer normalization on each element of the matrix. The fully connected layer is the same as the previous networks, except the activation function in attention-based neural networks. The activation function is GERU. Processing in memory refers to the technique that using memory to compute. This technique largely eliminates data movement between memory and processing units, thus improving performance and throughput. Let's take a matrix vector multiplication as an example. The matrix is programmed into the memory register first. The input vectors are transformed into voltage or analog signals bit by bit and are applied to the word line of the VRAM. At the bottom of each bit line, we can get the dot products. The memory register cell is essentially a metal insulator structure, which is simply an oxide material sandwiched by two metal electrodes. The current in immature fabrication and process variation often bring about hard faults, especially stuck at fault. Once a cell is identified as stuck at fault, its resistance cannot be changed. Therefore, the weight element cannot be programmed into the cell. A crossbar with incomplete matrix will definitely lead to accuracy degradation. The proposed accelerator mainly includes 8 components. Buffers and mask cache are used to store intermediate results to be used several stages later. The mask issuer generates mask according to input sequences. Crossbars are deployed to QKB agent, head merge agent, and fully connected agent to process matrix vector multiplication. The intra-encoder pipeline, and intra-decoder pipeline are shown on this page. Let's take the encoder pipeline. For example, in the first cycle, the Q vector is produced by the QKB agent for the first input sentence and is stored in buffer 1. In the fourth cycle, the layer norm agent reads Q1 from buffer 1 and writes its result to buffer 5. In the fifth cycle, the Q vector provided by the QKB agent for the fifth input sentence is able to be written to buffer 1 because there are no write after read headers in buffer 1. The structural headers appeared when more than one encoder layers or decoder layers are stacked to a network. Deploying too many hardware modules is energy inefficient. Through analysis, we find that 2 layer norm agents and 2 attention agents are enough to eliminate structural headers if we insert a few store cycles, such as 15 store cycles for transformer. The layer normalization is applied to all the elements of a matrix. First, both the mean value and the variance are calculated along the sentence axis. A sum reduction tree is implemented in this unit. Partial sums are accumulated in a register file. Second, we perform the normalization for each element. A set of parallel subtractors and dividers perform normalization. The lower figure illustrates our GLU design. The basic component in the GLU circuit is the exponent generator, which we adapt from an existing literature. This page shows our implementation. This page shows our implementation for softmax function. A sum reduction tree is implemented to compute the denominator, and a set of dividers work in parallel afterwards. To meet accuracy requirements, we conduct a small modification on the formula. The cell resolution of the VRAM we utilize is 4 bits. Hence, 2 adjacent cells on the same word line are leveraged to store high 4 bits and low 4 bits of 8-bit weight. The redundancy process can be modeled as a maximum weight matching problem in a bipartite graph. The whole process works as follows. Step 1, an algorithm first identifies the weight sparsity across layers. The layers are classified into different groups according to the weight sparsity. Step 2, the proposed algorithm takes in ReRAM crossbars information and the outputs of step 1. Step 3, the outputs of step 2 are different crossbar groups with distinguished storage capacity. Step 4, mapping the weights to crossbars. The benefit of the proposed algorithm is lowering redundancy ratio while meet the accuracy requirements. Algorithm 2 is a proposed non-uniform redundancy algorithm. The algorithm can be seen as subroutine. The algorithm 1 can be seen as subroutine, helping to update the states of the candidate crossbars. Algorithm 2 iteratively calls the maximum weight matching subroutine and updates crossbar state to get the final crossbar grouping results dynamic. In the left figure, the points on the horizontal axis represent the beta weights of input neuron and weights. According to the figure, we can conclude that accuracy loss is negligible when pruning weights and or quantization. The right figure shows the weight sparsity across layers. The vertical axis represents the percentage of pruned weights due to sparsity. We can observe that the layers close to the inputs are less sparse than the remaining layer. The throughput for Rx is only a quarter of that of the ideal. For the fixed crossbar, the Rx scheme can only store one copy of weight matrix, while the ideal scheme has 4 times the storage capacity for all benchmarks. Compared to Rx, ATT can store around 2.5 times the weight matrix, thus boosting the throughput by about 2.5 times over Rx for all benchmarks. This page provides a comparison of the speed up of both ATT and GPU implementation to both baselines. In general, ReRAM-based accelerator perform tens of times faster than GPU. ATT achieves better performance than the Rx, but still worse than the ideal. The left presents the power efficiency improvements. The values for the ideal case are theoretical maximum. The right figure compares energy consumption, including a breakdown into components. Although ADC and DAC are still high energy consuming components for all 3 schemes, we find the total energy of ATT is significantly reduced compared to Rx.
Thanks. I think we're a little bit tough in time. So anybody has a question? Please unmute. So maybe very briefly, what makes it specific to RNNs? Why is it not applicable to convolutional networks? Hello?
Attention-based neural networks use a totally different activation function, like GLU function, and the MATML involved in attention-based neural network involve two intermediate results rather than one weight and one input. I think that the 2 points are the main difference.
Okay, then given that actually the next session already has to start almost now, I would say if somebody wants to ask something, less chance. If not, then thanks to all 5 speakers, thanks to the attendees. Sorry for stealing the coffee break from you, and hope you can parallelize it with the next session. And this closes this session then.
Thank you.
Thank you.
Thanks.